This will be on some exercises that have to do with exponentials and logarithms in Chapter 2. We define logarithms to the base b of x to be this quotient. Now obviously this is 1-to-1 and maps onto r. Now why is that? Well, it's because this is just a constant, and this maps 1-to-1 onto r, and so this other one will also. Show it satisfies the same properties as the natural log, that is this. Well, this is kind of obvious because each of these is just a constant multiple of the log of x, and you know that the log of x plus xy is equal to the log of x plus the log of y. And I want to show that this is true and that this is true and so forth. Well, if you take b raised to the log of the base b of x, by definition of what you mean by raising to a power, this is the exponential of the log of b. Now you got to understand b is a positive number in all this. So this is exponential of the log of b times the log of x over the log of b, natural log. And you see these two cancel, and that gives you the exponential of the natural log of x, and that's x. On the other hand, if you look at this one, then by definition it's the natural log of a to the x divided by the log of b. And again, this in here, a to the x, that's by definition the exponential of x log of a, and then you have the log of b in the bottom. So the natural log and the exponential cancel, and that gives you this, and that's x times log of the base b of a. So you see, these kinds of properties follow directly from the definition. Now e, remember, was the number whose natural log was gave you 1. So if you look at log to the base e of x, it's the natural log of x over the natural log of e by the definition, and that's just the natural log of x because the log of e is 1, and that's how you defined e. All right, I want to solve this equation. Well, why don't we just reduce everything to natural logs? You can do it various ways, but let's do that. This other, where you have log the base 4 of 2 to the x, that's x, natural log of 2, divided by natural log of 4 plus 3x, natural log of 9 over natural log of 3. And you see, this just comes from the definition of the logarithm to various bases. Now, we know that this is equal to 2, and so x should be 4/3. Now, why would that be? Well, because the natural log of 2, if you take the natural log of 4, it's 2 times the natural log of 2, and those natural log of 2's will cancel. So you have an x over 2, and then similarly here you'll end up with a 6x. So you just have x over 2 plus 6x is equal to 2. Solve for x and you get 4/13. Or you could do this other way, all right? Natural log the base, log the base 4 of 2 to the x, that's x log the base 4 of 2, and I know what that is. It's 1/2, isn't it? And log the base 3 of 9, that's 2, so you have x over 2 plus 6x is equal to that. And now you can just solve for it. Here's another one. Show that for positive a and x, the log the base a of x is equal to this. So you see, we know that this is the natural log of x over the natural log of a. And now what I'm saying is it works if you use log to the base b instead of the natural log. Well, this is equal to this by definition, and these natural log of b's cancel, so that gives you this, and that's log to the base a of x. So I think this is very straightforward. So I want to look at log the base b of a times log the base a of b. Well, just put in what they are defined to equal. So this one is equal to this. This one is equal to that. And lo and behold, everything cancels and you get 1. Okay, I want to solve these exponential equations. So I will take the natural log of both sides. So that gives me 3x plus 1 times the natural log of 2 is equal to 2x minus 2 times the natural log of 3. And now this is just an easy equation that you've been solving since junior high, except that you have a messy looking constant here. So I just take all the x's and put them together and then solve for it, and here's what x is. Okay? And I want to see if I can solve this one now. Well, I will take the natural log of both sides. So that's x minus 1 natural log of 5 minus 3x plus 1 times the natural log of 2 is x times the natural log of 7. And again, just take all your x's to one side, take all the constants to the other side, factor and divide, and this is what you get. What about this one? Well, I can do it the same way. Take the natural log of both sides. So I have x log of 5 plus x plus 1 log of 7 is x log of 2, and then solve for x. And that gives you this answer here. I want to find x such that the log to the base x of 8 is 3. Well, what this says is that if you take x and raise it to the third power, you're supposed to get 8. That's really what this is saying. And so I know what x is. It's 2. Well, this is a similar problem. I want to take x and I want to raise it to the fourth power, and I'm supposed to get 1/16. So x should be 1/2. And then that will work, you see. All right, suppose you have 1 less than a less than b, x bigger than 1. How are they related? Well, what are they? This one is this. This one is this. The natural log of b is larger than the natural log of a. So therefore, this is the larger of the two. Okay, let's find log the base 3 of 27. I know what that is. It's 3. Log the base 2 of 64. What would that be? Well, it's the exponent to which you raise 2 to get 64. What's that exponent? 6. Because 2 to the 6th gives you 64. What do you raise 10 to get 1,000? 3. So this one would be 3. And what do you raise 1/2 to get 8? -3. So you see, these are all fairly easy things. Find the domain of x, of the function of x, given by this. Well, now, what we've got to have is we've got to have this thing inside has to be positive. Otherwise, you can't take the log of it. All right, so really we have to solve this inequality. Now, the places where this are 0 are -2, -1, and 1. And we also can't have the expression be 0 or undefined, because you cannot take the log of 0. So we need to look at the open intervals. The open interval from -2 to -1, that appears to work just fine. The interval from 1 to infinity works. See, if x is very large, this is going to be positive, so there's no problem. But these are only two that do work. You can check the other intervals. Look at x less than -2, like let x be a large negative number. This would be negative, this would be negative, this would be negative, so this would be negative, and you can't take the log of a negative. Okay, so you got to leave out all the stuff less than -2. And between -1 and 1, if you put in 0, for example, you'd have 1, and that would be top would be positive, this would be negative, and this would be positive, so you'd look at a negative number again, so you can't take the log of that. Okay, this one's interesting. Find the domain of this function. Well, what I need is I need to have this inside part, be bigger than or equal to 1. In fact, let's see, yeah, it could be 1. Why do I have to have it bigger than or equal to 1? Well, because the natural log is negative if the thing you're taking the log of is less than 1. And you can't take the square root of a negative number unless you go to complex numbers. And we don't want to do that in calculus. Okay, so what we need to have this thing bigger than or equal to 1. So what I'll do is I'll subtract 1 from both sides. And if I do that, I end up with negative 1 over x plus 2 needs to be bigger than or equal to 0. Now that requires that 1 over x plus 2 is less than or equal to 0. And so x is less than or equal to negative 2. However, I can't let x equal to negative 2, because if I do, then this expression will not be defined. You see? And so you need to have x strictly less than negative 2. Let's find the solutions to this equation. All right? Well, I would just write it in terms of natural logarithms. So there we are. And where I have this natural log of 2, that's the natural log of 4, and then I would have the natural log of x plus 4 over the natural log of 2. I just multiplied the top and the bottom by 2, so now I can just eliminate this denominator. And so I need to have the natural log of x plus 4 squared equal to the natural log of x plus 16. So since the natural log is 1 to 1, I know this needs to be that. Now when I solve this quadratic equation, it's got two solutions, negative 7 and 0. But I can't have negative 7, right? X can't be negative 7, because if I put negative 7 in here, where the x is, I'd be looking at the natural log of a negative number. So we got to leave this one out. It's not allowed. And so the only answer is x equal to 0. And if you check that, you see that it works. See, if you put in 0 here, you'd have 2 on the left, and you'd have 2 on the right. If the interest rate is 4% compounded continuously, how long does it take a given amount of money to double? Well, you need to have 2 is equal to e to the 0.04 times t. And now you need to solve for t. So how do you do that? You take the natural log of both sides. So you have the natural log of 2 divided by 0.04, and that's 17.329. The population of bacteria grows exponentially. It's observed that every hour this population doubles. How long will it take to have 8 times as many bacteria? Well, I think that's fairly easy. You have an amount times 2 to the t. That gives you the amount at time t. So you need to have 8 is equal to 2 to the t, and obviously t should be 3 hours. Pesticide has half-life of 27 years. How long will it take to have only 1/4 the initial amount? Now, you can go through the reasoning here. You see there's going to be a constant of decay. You can compute it from the information you're given and work it out, or you can just think of it this way. The amount of it is cut in half every 27 years. So in 54 years, it will have been cut in half twice, and that would be when you'd have 1/4 the amount. And if you go through the details, it works out that way also. Now suppose you have 5% interest and it's compounded continuously. You make a payment of $100 at the end of every year, starting with an initial amount of $1,000. How much will you have at the end of 10 years? Well, you'd have the $1,000 is going to accrue interest, and since it's compounded continuously, you'd have 1,000 times e to the 0.05 times 10. All right? Then you'd have your first payment at the end of the first year, which is $100. And that would be, how much would that be at the end of 10 years? E to the 0.05 times 9. And then you'd have your second payment times e to the 0.05 times 8, on up until the last payment at the last end of the last year, which is $100. And so you need to sum all these together. Well, you have this one plus this, and this is just a geometric series, and we have formulas for that that were developed in Chapter 1. All right, so this expression here is 100 times 1 minus 1 times e to the 0.05 to the 10 over 1 minus e to the 0.05. And now if you work that out, have the calculator do it, you find you get $2,914, which is good. So you picked up a lot of extra money because of the interest being compounded continuously. All right, you take measurements. Suppose measurements are taken of an exponentially decaying substance. It's found that after 5 years, there's 0.9 of the amount which was present at the start. What is the half-life of this substance? Okay, what we do is we use the given information to compute this decay constant, K. So the decay constant, I'll take a log of both sides. The decay constant is a log of 0.9 divided by minus 5. And now, for the half-life, we would put 0.5 here equal to E, and here's the decay constant, e to the minus that decay constant, times t. And so then I take a log of both sides, and so t is equal to the log of 0.5 divided by the log of 0.9 divided by 5 here. That's the decay constant. And if you work that out, you get 32.89 years. See? Okay. Here's the logistic equation. Suppose you know that initially you have 20, and that k is 30, and that r is 1. I want to find c in the logistic equation to conform with this information. So I look at this initial condition. So I have 20 is equal to 30 over 1 plus c times 30, because when I plug in t equal to 0, I just get 1 there. Then I solve for c, it's 1/60th. And so now here's y as a function of t. It's 30 divided by 1 plus e to the minus t times 1/2. Now if you want, you can graph this. It will approach 30 as t increases. So you'll have a horizontal asymptote, and 30 will end up being the maximum possible population. Okay, in the logistic equation, explain why for large t it will always be close to k. Well, I think that's what we just talked about. See, this is the solution to the logistic equation. And so as t gets very large, the e to the minus rt drags this whole term to 0, and so the whole thing gets closer and closer to k. Now, suppose that you have any function. You can always look, and it's defined on the real numbers. You can always look at an odd part and an even part. The even part is 1/2 times f of t plus f of minus t. The odd part is 1/2 times f of t minus f of minus t. So, this h of t, which is the even part, I say that's even. Why? Well, because if I look at h of minus t, I would now replace everywhere I see a t with a minus t, and I get back h of t. So you see that's what you mean by even. G is odd because if I plug in minus t in here, in the formula for g of t, I would get f of minus t minus f of t, which is just -1 times g of t. So you see, it's odd because when you can factor out a minus sign, see, and have g of t left. Okay, now you know that f of t is equal to this plus this, and that's why this is called the even part, and it's called the odd part. Now, an extremely important example that people use a lot are the hyperbolic cosine and hyperbolic sine. And they're really just the even and odd parts of the exponential function. And now that's all we have for chapter 2.